here now we are going to just consider Schrodinger equation because it's, if you can solve the Schrodinger equation problem, you solve the previous problem. Okay? So just consider Schrodinger equation. And also you can see that in the connection, what is Q? Do you still remember for the conductivity equation, how the conductivity equation reduced to that? There's a connection, from the conductivity to the Q, remember that this straight
delta over square root of R.
This square Laplace.
Yeah. Laplace R.
Now this is an observation. There's no logics behind that, which will help you to get it. Okay, it's an observation. You see, when you study mathematics, your teacher gives you things to prove, right?
Yeah.
That's only the part of reasoning, right? But in the research, this is only a small portion. The main thing in research is observation. You have to do some investigation to find out something behind, and they try to verify it with reasoning. Mm-hmm. So reasoning is basically a verification process. It's not a main thing in the research. You have to discover something. Okay.
Trying things over.
So that's why that's how you can discover things. You have to be getting more and more experience, more familiar with the field areas. Okay. So here, so this is something people discover. Okay, not follow from a lot. Okay. But anyway, so you can see that. But however, if you have a conductivity reduce this Q, then for this Q, this equation always has a unique solution. Right? So that means that 0 is not an eigenvalue to these problems. Okay. But however, suppose we just talk about the general Schrodinger equation like this. You have to add additional condition on Q, assuming that the 0 is not an eigenvalue. You have to assume that. Once this assumption, then you can talk about like a V on the boundary equal to F. You can, so this problem will be uniquely solvable. Then you can define the linear map for these equations. Is lambda Q is from F to B, B, E, N on the boundary. Okay. So this is the corresponding linear map for the Schrodinger equations. So the question is, so the main question is whether the map Q to the lambda Q, okay, is injective. So this is called a uniqueness question for this inverse problem. And for the inverse problem, we know that the central question is uniqueness question, not existence. Okay, now if this question is solved for the Schrodinger equation, then you can use this result to get the uniqueness result for the conductivity equations. So that's why this reduction is so important. And so now we are focusing on this question. And also last time we talked about linearization process, right? The Padron first used the linearization process, but that process only gave us small information, a little bit information, does not help us to handle this nonlinear map. Exactly. So in order to solve this problem, you cannot just use the linearization process. There's a reason behind this. We covered that this last time. So today we have to find out exactly how do we prove that. How do we handle this nonlinear map directly to show that it is injective. Okay. Now the key is that if you think about this, here this is the data we have. Okay. Then from this data we're trying to recover Q, right? So that's the physical problems. But in order for this recovery is possible, you have to show that this is unique. This map is unique. Suppose you have another Q, also goes to the same place to the map. the changes to be mapped on the boundary, and these are Q are different, then recovering is impossible. Which one to recover? There's no way you can construct a reconstructing process, right? So therefore, that's why the uniqueness is so important here. Now, in order to choose uniqueness, so you have to connect. You have to connect your data. I mean, this existing information from the unknown, right? So you have to make some connections, okay? Some identities or some process that's connect this potential with this to the map. Then you can see whether this map is injectable. Now, without this relation, then you can do anything. You cannot do anything. Okay. But fortunately, there is an identity connecting these two things. There's an identity. Okay. So this is the first we want to talk about today. So here is identity. That's important identity. Okay. Again, this now this one discover this identity. The process is easier than discover this relationship. Okay. Now the identity is that suppose you have two equations with two different potentials. Okay. So so you have two equations like this. Laplace VI minus V1 minus Q1 V1 equals 0. So for the first equation, I use V1 to denote the solutions, okay? And on the boundary, V1 is equals to. Now here, we always talk about the strong solution. Now when we talk about strong solution, automatically we call the weak case. Okay, so it's C2 equal F1. Okay? And you have another Q2, another potential. Okay? So V2, you omega F2. Now the reason I'm putting the boundary value is because that we're going to use these notations. The main thing is that these two potential create two gears to be right? Or the first being Q1, lambda Q1, then here you have lambda Q2. You have two different boundary maps involved. Okay. So here is just notation. So the Q1 goes from where to where? Lambda Q1 takes the F1 to the normal derivative of B1 on the boundary. Okay, and this one takes F2 to the normal derivative of B2 to the boundary. Okay, now suppose, so we're given these notations then, so there, actually you can see that there's no any restriction here. I just suppose I use this notation, and that's it. Okay, then I can establish a nice relationship. Is a identity, which is given by integration. So it's the Q1 minus Q2. Now that's the things we try to shoot to be 0, right? But if I want to shoot that this is injective, that amounts to shoot that if lambda Q1 equals to lambda Q2, then Q1 minus Q2 is 0. That's exactly what we want to shoot. But this identity exactly gives you this quantity. So that's one of the amazing things. Then V1, V2, V1, V2 equals to the corresponding solutions, okay? And yes, now this equals to the boundary integration. The F1 lambda Q1 minus lambda Q2 applied to F2. Yes. So that's our data. So you can see that here, this is model, the integration over the omega, okay? So it's equal Q1 minus Q2. So the product, so on this side there's another product, is the product solutions coming from two different equations. Okay, V1, V2, okay? then this integration turns out to be equal to a boundary integration. Takes the difference of the Dirichlet-Neumann map applied to F2. Okay? Now if you take this boundary map applied to F2, what do you get? What do you get? Another boundary function, right? Another boundary function, okay? Or you can say this is another boundary function. Then times another boundary function F1. This product, you take integration. Okay? This boundary integration turns out to be equal to that. For any F1 and F2, there's no any restriction. This is a very, turns out to be very useful identity. And the proof is not difficult. It's just integrated by half. But the difficult thing is how do you use this to get what we want here. So I'm going to first prove this, okay? Prove this is you take this equation. Okay? You multiply the V2 on both sides. So you have V2 plus V1 minus Q1 V1 equals 0, right? Then here, so it's create two terms. The first thing is V2 plus V1. Then another term is Q1 V1 V2. Q1 V1 V2 is fine, it's already there. Now here, the idea is for the first time you have the Laplace here, we're trying to shift the Laplace into V2. You can do this by integrating by half, twice. Okay? So I'm going to do this. So Laplace, so I shift this to the V2 times V1. And then plus what? I mean, the Laplace can be written by gradient dot to gradient. You do it one at a time, right? So if you involve the first one, you actually apply the gradient to that, but you have to adding a term like this. The gradient of V2 to the gradient V1, right? Okay. Then the next one, you take the second gradient to the V2. You have another term, which is minus. Here's V1. So after the first one, you get this. Then you put this one again to here, so you get the minus gradient, then the V1 the gradient to V2. Okay? Then finally minus Q1 V1 V2. So here is just the product rule, basically. Right? It's a product rule. Then you do the integration on these four terms. Then you can see these two terms by the diverging theory will reduce to boundary. Okay, so therefore you're going to have this the lambda Laplace V2 V1. Okay, then I put this one together with this, so minus Q1 V1 V2, and this one you have the dx. Okay, then plus the boundary term d omega, then V2 dV1 dn. Okay? Then also to this one is that the V1 dV2 dn. Yes. Right? Now here is just diverging theory. Now here, Laplace V2. Now Laplace V2 satisfies the second Schellinger equation with Q2. So this term can be reduced by what? By Q2 V2, right? So this one, so you here is Q2 V2. So the first term in the first integration is Q2 V1 V2. Yeah. Okay, so now you can see that they have a common product, V1, V2. Then one is with Q1, the other with Q2. Okay, so if I move this term to one side, to the other side, okay, keep this term on one side. They are okay, this equals 0. So move this to the right side. Okay, then for the convenience, switch both sides. So what do we have? This integration of Q1 minus Q2 Q1, V2. Yes, is equals to the integration on boundary. Now here we have to understand this. Now here, dV1 dN, that's a normal derivative on the boundary, which is equal to what? This is equal to lambda Q1 applied to F1, right? Okay, so here is the F2. So once reduce the boundary, V2 reduce to F2. So lambda Q1 F1, okay? Then minus, then here, V1 become F1. Then this one is just equals to the lambda Q2. Lambda Q2 to what? To F2. Yes. Okay. Right. So far everything is so elementary. I mean nothing fancy here. Right? But the thing is, you can see there's a trouble getting here because here lambda Q1 and lambda Q2 is supposed to can put together. But here lambda Q1, I do have lambda Q1 and lambda Q2, but they do not apply to the same boundary functions. Okay, I need to fix this. To fix this is we have to realize that this identity is so far this identity works for any potential Q1, Q2. Okay, for any potential Q2, right? So I take a look at special case. So when Q1, Q2, Q, suppose they're exactly the same. Now what kind of consequence getting from here? Then the left side becomes 0 because Q1 and Q2 becomes 0. Now how about what is message coming from the right side? The right side means this, the omega. Now F1 and F2 will take the same because it corresponds to the same potential. So F lambda Q is the same, just right? And F. Also, sorry. Q1 equals Q2, okay? The same equation, that means same equation, but I do not want the F1 and F2. I'm consider F1 and F2 are different boundary functions, okay? Okay, then you can see this will become F2 lambda Q F1 minus F1 lambda Q F2. Yes. Okay. Now what does it tell us? This basically tells us that this boundary integration of 2 lambda Q F1, yes, is equals to this d omega F1 lambda Q F2. Yes. Now this is an important message. What does it tell you? That you see F1 is not equal to F2, right? But they can switch. One inside and the outside can switch without changing value. They're symmetric. So if you think about this bilinear map on F1, F2, then this map is symmetric. Okay. Now because of that, so apply this here, you can see, apply this term. Okay. Or you think about this term. So you can see, you can concentrate on lambda Q1. Okay, lambda Q1. So this result tells us that I can switch to F1 and F2. Okay, right? Now if I switch, then you can see that this will become F1, then this one will become F2, right? Mm-hmm. Then here is also F2. So they have a common factor. You can take this out. Once they take it out, this is exactly the right side integration. Yeah. That's it. So that's a proof of identity. It's very, the proof is very elementary. Nothing. I mean, basically, it's just computation. So.
What's the name of this identity?
Okay, so this identity turns out to be very important because from this identity you can see that you can have the consequences is that if lambda Q1 equals to lambda Q2, then what can you say? Then the right side becomes 0, right? So this means that the integration of Q1, Q2, the V1, V2, yes, equals 0 for all solutions V1, V2. So at least I get a result relating to the Q1, Q2. So we hope to show this will imply to Q1 equal to Q2. Right? We hope to show that. So from lambda Q1 equal to Q2, we wish to show that this will imply that Q1 minus Q2 equals 0. Okay. You see, here it's involved the product of solutions here. So for this purpose, let's do the notation. So it's the P, Q1, Q2 is equals to all the product of solutions. I mean V1, V2. Such that VI is the solution. Is the solution to the Schrödinger equation. Okay, you take, I mean here, V1, V2 corresponds to different potentials. Okay, V1 corresponds to Q1, V2 corresponds to Q2, right? But here, you take arbitrary solution from these two, right? They multiply together. If you multiply together, you have a one product, right? But you have an infinite number of choice of the solution you have. So you have infinite number of product involved here. Okay, so this is a set in a function space. So any product is a function, right? So you put all these products together, it forms a set of functions. So I'm going to view this as a set of functions in L2. Because if you have a strong solution, so these are the C2. So there's no problem there. I mean, to become the product is become an L2 function, there's no problem. Okay? I consider this as a subset in L2. Now, with this notation, what do you think? What kind of property we need to establish for this subset so that this will imply that? It's a complete set, right?
Yeah.
If this set turns out to be a complete set, the set may not be a, well, obviously there's a product, it's not going to be linear space, of course.
Yeah.
Well, you can expand this as linear space, but it's not a big deal. But the thing is, if this is complete, if so, the completeness of P, Q1, Q2 in L2, suppose you can prove this, but I don't know yet. I don't know yet. So this will imply that the uniqueness. Uniqueness means that this map is injected. Okay. So if I can prove that, then you can see that the uniqueness problem is solved. The uniqueness problem is solved. So everything now is reduced to the product solutions. So you have to know a lot of, so you need to know better about the Schrödinger equation to show that the product, okay, the product is actually complete in L2. Then that's, once this is proven, then we have an answer to this question. Okay. Now, so the next step is to see how this will imply that the product of solution is complete. Now, at least in dimension greater than or equal to 3, everything can reduce to that. Okay, about reduce to this. In dimension 2, there's a harder way to approach to the uniqueness. As we can see last time, in dimension equal to 2, the problem is formally determined. It's not over 2. Okay, so that's a harder problem. But at least in the dimension 3 or higher, then we can show that. We can show that this set is actually complete in L2. But however, there's a harder work. It's not easy to prove that because what? So for elliptic equation, how much information you know about the solutions? You can only have some quantitative properties, like the maximum principle and like the Hanna inequalities, something like this. But if you want to come to the to get information about completeness of product, then you have to use some other unknown information about the solutions. Okay. So the way to handle this is to construct what we call the exponentially growing solution to the Schrodinger's equation. So this is the next thing to try to introduce. So you can see that, let's look at the general Schrodinger's equation like this. Okay, general Schrodinger's equation. And we know that, so this equation can be considered, I'm going to compare to a Laplace equation. Okay? And so for Laplace, so the question is, so somehow you can think about this Schrödinger equation is a perturbation of the Laplace equation because you're just adding up 0 of the term, right? Okay, for Laplace equation, Calderon's work provided one clue because his linearization turned out to be, he discovered for Laplace equation solution like that. V equals to E C x dot x. And C is in Cn, with a complex vector. Okay? And with C dot C equals 0. I mean, he found that as long as you take any complex vector with this condition, then this function will be automatically a harmonic function. But this harmonic function is not a real function. It's complex.